Good morning. Welcome to the tutorial on large-scale visual place recognition and image-based localization. This will be given by Alex Kendall, Giorgos, Tolias, Akihiko, Torii, and me. We're roughly going to cover two things. The first one is visual place recognition, where we're given a query image and a database of geotagged images. And given the query, we would like to figure out which place is depicted in this query. We'll retrieve the most similar image from the database and then use this to get information about the place and a rough approximation of the camera pose. And this part will be given by Akihiko and Giorgos, where Aki will cover the classical feature-based methods and Giorgos will cover learning-based methods. And then the second part is about precisely estimating the camera pose given the query image, for example, relative to a 3D point cloud. And this part will be given by me, where I'll cover standard feature-based approaches, and Alex, who will do learning-based methods. Schedule is we are going to start with feature-based methods for place recognition, then do learning-based approaches for this, do a short coffee break, and then start with visual localization for accurate pose estimation. As said, there are essentially two parts. The first one, we're more interested in what the query depicts, and only roughly in the pose or the position and orientation from which the query was taken. So this part is typically solved as an image retrieval problem. And then in the second part, we would like to precisely locate the position and orientation of that query. So for example, in the context of AR, VR. Why should you care about it? Well, I guess you're all here, so you do care about it anyways. There are a couple of cool applications for this. So one is tagging or geotagging holiday photos, where, for example, you can upload this very nice application from Noah's Navely, where you can upload pictures and then get a very precise geotag. The second is visual information retrieval, where rather than searching for a term, you have a picture, you search with this picture and that get information. For example, here the closest street view image in Tokyo. But it could be more than just a position. And I believe that an important part of visual place recognition, visual localization, is not necessarily placing a camera accurately, but more getting information about the surroundings. So what are you seeing? So this is, for example, this is an example where you could take a picture, send it to an information retrieval system, and that get fine-grained information about what's seen in this image. So on the left you see the Arc de Triomphe in Paris, and on the right a mural that I can't place at the moment. You could also look at use place recognition techniques to locate images over time and track the development of a place over time. Self-driving cars are another application for image-based localization, where you precisely would like to locate the car. So this is a project we did at DTH a couple of years ago, where we were aiming to build a self-driving car, but not solve the full problem, but more a car that you could leave in front of the parking space, automatically get a parking spot, drive there, park, and come back once you needed it. And in order to navigate through this indoor parking space, you need a precise position and orientation information, and you can't rely on sensors such as GPS because they're just not available. Augmented reality is another application for image-based localization, where you would like to figure out where the camera is with respect to some representation of the scene. And if you know that precisely enough, you can project virtual objects into the scene. And if the pose estimate is stable over time, and it is as if they were part of the real scenes. So this is something that we did a couple of years ago. We were by then able to manage to run this in close to real time on an iPad 2. We couldn't do this on iPad 2 footage back then because the rolling shutter of the camera was too severe and we didn't want to spend some time on this. By now we have a more advanced version of this running on a Google Tango tablet. And here's another application for augmented reality where you could use it for navigation in indoor scenes. Here, for example, this is someone being led to a chocolate shop in the main station in Zurich. And well, it's Zurich, so it will lead you to a chocolate shop, but essentially you could also go to other places. And the last example, or application example that I want to show is virtual reality. So this is a master thesis that a student did with me, where he first scanned a room to create this virtual model on the right that kind of reflects the properties of the room. And then this virtual model is geo-registered. So by tracking the position and orientation of the headset with respect to this room, you can track the movement of the user in this virtual world, meaning that you can start walking through this. And so far, this is just a proof of concept showing that you can do this. Ideally, you would like to have the possibility to interact with the scene, but we are not there yet. So the current interaction mechanism that we have is sitting down on chairs, which is a bit strange if you can't see your own hands. But this is one application example. In general, before Aki starts, the slides will be available on the tutorial website, and the tutorial should also be available as a video later on the CUPR website. So thank you very much, and enjoy the rest of the tutorial.
Okay. Hello. Yes. Hello, everyone. Thanks again for coming this tutorial. Okay. Yes. Can you hear me? Okay. In this first session of tutorial, I'm gonna talk about feature-based place recognition. My session will be more to the beginners or who don't know about instance level recognition, image retrieval, place recognition. So I'm afraid this session might be a bit bored for the experts, but I hope my session will be take a role as a guide for advanced deep feature-based methods or 3D-based methods. So I hope there are still nice things for the feature-based image, classic feature-based approaches, as we can discuss about later or probably in the panel. So this is the table of contents of this talk. I will first talk about the goal of visual place recognition in the introduction and discuss about what the challenges are. Next, we review the local feature-based image representation, which is commonly used in the place recognition program. We then introduce how we customize or optimize the standard image retrieval method to the place recognition programs. Then I will finally introduce the common data set, which is available publicly, and some which should be useful when you want to evaluate your method in the place recognition framework. So let's get started. So now we would like to consider the task of visual place recognition, where the goal is to recognize the place where a given image is taken. We would like to input image into the search box and get its location as the output. So to address the place recognition task, the common approach is to cast as visual instance recognition. So in a bit more detail, the standard approach is summarized like this. First, the world is represented as a set of geotagged images. Of course, this should be done offline. Then, given a query image as input, we seek for the best matching image in the database. Again, finally, we transfer the geotag of the best match. This is an example tag. Actually, this tag address is the address of the Google Street View, which has some GPS information, and actually, it also has the orientation. So, oops, sorry. Now, I want to discuss why is this interesting. Photos, images, videos are everywhere nowadays. I cannot really organize my thousands of photos of my kids. But actually, for the personal photos, it should be okay to organize by time because you you can look back into by time. But if you want to archive any historical photos and want to archive it for the next generations, I think it will be meaningful to organize on the map, on the globe. So I think visual place recognition can do that job, and we can localize, we can essentially localize the photos taken at all time, or even the scans of the photos. So also another interesting point is that we need to study both recognition and geometry, which are very interesting to me, because in other words, standard image retrieval often focus on the image appearance only. But to work on this place recognition, we have to deal with 3D geometry and also the distribution of the images on the globe. So I think this is a bit different, and I like this topic. So maybe I will skip this. So before going to discuss about the challenges in the place recognition, I just want to quickly mention about the synonyms. Some papers call this problem, like us, as place recognition, but some calls location recognition, landmark identification, or geolocalization. I think there are some small differences, like the expected final accuracy of the localization or recognition, but I think essentially we are all tackling to the same problem. So let's next have a look at why the large-scale visual place recognition is challenging. Before thinking about that, let's have a look at the source of geotagged images. There are two major sources. One is the photo community sites like Flickr and Instagram and so on. The good point of these community photos is that it is never stop going. So people keep uploading the photos. So that means there are many photos taken at different times and different viewpoints. But the images and their geotags are often noisy or contaminated. So we have to do some pre-screening if we want to use those images as a database. The other main source is Street View images, like Google Street View. Such images are accurate and cover almost all the street. but it is updated less frequently. Of course, we have to drive every street. So both can be the sources of the place recognition works, but here we want to do street level recognition. So we should use, if we want to do the street level place recognition, we should use the street view images, of course. Okay. I also have to mention that.
Excuse me, can I ask a question?
Oh yeah, sure, sure.
So I'm not sure actually if Google Street View imagery is publicly available. So is this the case or no?
So available?
Is this Google Street View imagery publicly available for research, or I'm not sure if it's the case.
Okay. So from my asking to the Google, or our group asked to the Google, so the current understanding is it's fine to use for the research purpose. So we can somehow scrape the images from the Google Street View website, and we are using it. But of course, maybe it's not good for the commercial services. So I wanted to mention that most of the cases, the query images are perspective. So it is natural to prepare the database images as a perspective images. But the Google Street View images has this equirectangular panorama. So we usually prepare the perspective cutouts like this. So now let's have a look at how many images are needed to cover a certain area. The largest dataset used for street view place recognition is the San Francisco dataset, which covers 6 square kilometers and consists of 1 million images. The 1 million images are not too large for the recent image retrieval techniques. But acquiring and capturing those data are quite difficult. So maybe in near future, if autonomous driving develops and if we can collect those information to the database, the images, database images will be spatially and temporally denser. However, in the current technologies, it is impossible to monitor all the streets every time. So that makes the gaps between the query and the database images. So the gap means database images are taken temporarily sparsely, but query could be taken at any time. Even for short time changes, there will be large illumination changes between day and night or weather condition. For long time, there will be seasonal changes such as tree coloring, snowing, and also structural changes. So as we cannot capture the database images from all the possible viewpoints, there will be always viewpoint changes against the database images. In reality, we have the mixtures of these changes. There will be a large gap in appearance between query and database images like these. In addition, if we want to do the large-scale visual face recognition, it makes the problem even more challenging, because we have to deal with the problems of repetition or memory requirement and so on. But thanks to the advances of image retrieval techniques, we can do the place recognition at some level, even now. So there are no technical details, but if there is any question so far, okay. So now I'm going to review the local feature-based image representation, which are commonly used in the place recognition. in the visual instance recognition, given a database of images, we design an image representation extractor function which can provide a mapping from an image to image representation space. Then all the database images representations are extracted offline. When the new image is given, we extract its representation and find the closest database representation and transfer its location. Okay, so the state-of-the-art local feature-based approach is start by extracting local features like SIFT. These are then aggregated using Boggle words, blurred feature vectors to obtain the final image representation. There are many improvements to this basic pipeline, such as spatial verification and query expansion. So first, we give a short review of this Boggle words representation. This is one of the most well-known approach. So Boggle words starts by quantizing the descriptor space using k-means. Descriptor X is extracted and assigned to its closest cluster, denoted with the assignment variable AK here, which is 1 or 0, depending on whether the cluster K is the closest cluster to the descriptor X. Then all the descriptors in the image are assigned to their closest clusters. The assignment variables are summed up, which basically counts the number of descriptors assigned to each cluster. The counts are then concatenated to form Boggle words histogram. So this is the basic idea. So next, a more recent aggregation method is blurred, where a descriptor is assigned to its closest cluster, as same as Boggle words, but extra information is kept in the form of the residual in this way. In other words, the distance between the descriptor X and the cluster center CK is stored. So to compute a blurred image representation, all the descriptors are extracted and assigned to their closest clusters. Their residuals are summed up and concatenated to form the final blurred vector. The motivation behind the blurred is that it stores more information than Boggle words because it saves the location of the descriptors in the descriptor space than just simply counting the number of words. So in the terminology of the CNN, this blurred or Boggle words can be seen as a powerful pooling method. So here is the comparison between Boggle words and blurred. For Boggle words, it is good to use large vocabulary because it makes the histogram sparser, and then you can efficiently implement with the inverted indexing. Another good point is that Boggle words matching is essentially the feature matching with quantization. So it can naturally provide a feature-to-feature matches. That means, so let's say left is a query image, right is a database image. So if the features match in the same visual world, we can just connect it and we can use as a feature-feature correspondence. There may be some multiple features assigned to the same centroid. Then in this case, we have to pick one, or we can just make many correspondences. It's just a matter of your choice. But essentially, those feature-to-features correspondences can be used the following ransacking or spatial verification. So this is quite useful. So next, on the other hand, the blood performs quite well, even with a small vocabulary. Actually, this is important because we have to assign the features to the centroid. If the vocabulary is large, it takes some time. Of course, we can use ANN and so on, but still smaller is better. But even with small vocabulary, blood works quite well, as good as large vocabulary Boggle words. And it is known that blood can be further compressed by PCA with negligible loss of the performance. Okay, and another good point of the blood is it does not increase the memory footprint even if you use many features. But in other words, it is not a good idea to use many features to represent in a Boggle world, because then Boggle words will be very dense histogram, and so you cannot be efficiently compute with the inverted indexing. So this motivates us to use many features for the blood. For example, instead of using local key point detection like DOG, we can simply use dense shift, which is a shift descriptors densely detected on a regular grid. When we use dense features, we lose a viewpoint invariance somehow. But for the place recognition task, which is actually okay, because what we want is we want the image from the same view. So we don't need an invariance of the viewpoint changes so much. And this, in fact, this dense-based representation naturally leads to the recent CNN-based representation, because like NetBlood, because we can regard the convolutional layers as a densely described features. So it is quite natural to extend to the CNN-based representation. So now I'm going to explain about how to extend these standard techniques to the place recognition. But if you have any questions, I'm happy to take some. Okay. Okay, so let's move on. So I would like to talk about how to customize or tailor the standard techniques to the place recognition problem. So now I'd like to review a bit about Boggle words representation here. So please forget about the blood for 5–10 minutes. So in general, there are quite a lot of techniques to boost up the performance of Boggle words image retrieval. We should, of course, adapt such techniques which are suitable for, if it is suitable for the place recognition. And if that can address these problems by the large changes in appearance. So the first problem is in the modern city, there are many repetitive structures, as you can see here. This makes a serious problem for Boggle words matching, because the features detected on such patterns saturate the histogram and dominate the similarity scoring. So there are known methods called burstness weighting that simply suppress the overweighted histogram. This is very effective actually in the place recognition task. Another technique is soft or multiple assignment. As we are using quantized feature space, the assignment will be erroneous close to the boundary of the feature, these clusters. in other words, assignment is unreliable if the feature is far from the cluster centroid. So this can be solved by multiple assignment. In the multiple assignment, the feature is simply assigned to not only the first nearest neighbor, but for the second, third nearest neighbors. And optionally, you can compute the distance to the centroid and use it as the weights of the visual world counting. So on top of these state-of-the-arts, we developed a fusion of these techniques. We call it adaptive assignment. In this method, we first detect repetitive patterns in the image explicitly and group them like this. So this can be done using visual world clustering and using spatial position, looking at the spatial position of the features on the image. Then we deem it as an important and distinctive feature if it belongs to the small clusters. So if it does not belong to the repeated patterns. Then for such things, we do the multiple assignment. So but for the features grouped to the repetitive patterns, we don't do any multiple assignment because it will again increase the pause in the histogram. So this is in the end simple technique, but it works quite well for this street level place recognition task. So yes, okay. There is another nice technique which is called humming embedding, but probably I will skip this because I'm running out of time. So, but basically the idea is this method subdivides each Voronoi cell into a lower dimensional subspace and give additional signature, which is binary. So this can measure the distances between the visual world matches more precisely, but it doesn't require too many memory space because it's just binary signatures. So this is another extension, and there is a method called dislocations, which is an extended version of this humming embedding, but I will skip this for the time. So if there is any questions so far? Okay, so the approaches I have introduced so far are sort of modification of the general image representations. But the database images are geotagged. We can use that information to improve the place recognition performances. So then how we can adapt such geographic information in this task? The key idea is that spatially far images should not match. So this is simple, but it's a good idea, I think. So for example, the image here, so if you extract some features on the image here, the feature should not match from elsewhere if it is distant. So this idea has been used in earlier works, and based on this idea, we can do many things. For example, we can detect confusing features on the image, such as trees or repeated patterns as well. So in this method, they explicitly do the feature matching between the image and the image samples from the distant location. And then find the areas which has high density of the local matches. Then we can compute the confusion scores for every region and make a kind of mask. So I don't know if the contextual weighting presented on Monday is inspired by this method, but I think there are some relations to the recent modern CNN-based masking or finding confusing places, and these classic approaches. So the same idea was used in different approaches, such as learning per place linear SVM, or also we can use for making the positive and negative examples for training CNN image descriptors, like NetBlood. So the conclusion here is that it would be particularly interesting to use these location players if you want to develop some new place recognition techniques. Okay, so next I want to discuss about how we can deal with major changes in appearance. For example, images include large illumination changes like day, night, or seasonal changes. So these problems across the time and seasons are also often studied in the robot vision communities. For example, Modern generates illumination invariant images by converting RGB images to the kind of illumination free image using the sensor information. NewBot uses repeated recording of the sequence of images across the seasons. Assuming that the images across the different seasons are aligned, they can learn the transition of the visual world across the seasons. So then, for example, given the query images of the summertime, they can transfer the visual world to the winter version and search for the winter database. We also try to address the day-night illumination changes. To do that, we first generated a very challenging data set that contains major changes in illumination as well as structural changes. The main observation by studying with this data set is that dense shift can cope with large changes in appearance and illumination. So that means the descriptors are quite strong enough for the illumination changes. But this local key point detection is quite weak to the illumination changes. So we tried a simple experiments that is, so left is a query image, right is a street view image. We run the standard feature matching with Landsat-King. And this shows the, and we evaluate the number of in-layer matches that can indicate the difficulty or easiness of the image retrieval. Because if the in-layer rate is high, we can easily retrieve the images because that's a trick. So for the, if we use the sparse features, it's very difficult, the in-layer ratio is quite low, like this. But once we switch to the dense shift, actually the problem becomes much easier. Then if we synthesize the image and generate the view close to the query image, then the problem will be a bit easier even for the sparse features. So if we combine them, synthesizing the viewpoint and using the dense features, the problem will be much easier. So from these observations, we decided to explicitly generate synthesizer views and add them on the database images. So originally we have these street view images on the red dots, But we generate synthesized images on the gray dot positions. To do that, we use the depth map associated to the panoramic images of the street view. Actually, you can get a depth map as well from the street view. Then we generate this kind of synthesized images. So we did quite naive synthesis, so there are many holes and the quality is not that great. But this is already sufficient for the place recognition task. Okay. So this is the result. The left column is the query images, and the second one is the one retrieved from the synthesized images. So as you can see, there are less viewpoint changes between them, and we can match well, quite well. But if we use only the original images, those images are matched, which is wrong. And these are another examples. So as you see, the quality is not that bad, but if we encode to the blood and dense shift and blood descriptor, it works quite well. So as the last topic of this session, I'd like to introduce the datasets available for the benchmarks and the standard evaluation protocol. But okay, yes. Okay, so yes, okay, I don't remember the number exactly, but I think I expand the database like 10 times. So the database becomes very large. But as we are using the blood compression, so the increase is quite fine. And also, if you can use product quantization, there we can also suppress the memory footprint. Okay. Okay. So as the last topic of this session, I'd like to introduce some datasets available for the benchmarks and standard evaluation protocols. So there are quite a lot of benchmark datasets, and as I just explained, we prepared this Tokyo dataset, which is quite challenging, and the size is not very large, but the query images has these illumination changes. And I just show the standard Oxford Paris because it's also the dataset with a building. And there are datasets for the 3D based approaches. Actually, for the 3D based approaches, there are quite a lot of them, including the San Francisco and the others. And there were new dataset presented the day before yesterday, I think. There were some new Baidu dataset, and so on. Okay, so if you want to evaluate your method, I would recommend to use, of course, our Tokyo dataset, and also the largest San Francisco dataset. And the good thing of the San Francisco dataset is there is some 3D reconstruction too. So you can compare with the 2D and 3D method. So actually, for evaluating your method in the place recognition, it is reasonable to evaluate the recall for evaluating your performance. But the evaluation protocol differs by the ground truth. So I thought I prepared it, but I lost it. Okay, so the San Francisco dataset gives the labels of the images as a ground truth data. So each database image has building ID, and query has several IDs. So if you do the image retrieval, and if the ID match, we can deem as a correct match. So this is the way of evaluation. And you can computer recall with respect to if your retrieval succeeded or not, and draw some graphs. And for other data set which has the GPS position as a ground truth, we can just threshold it, and we can use them as a label if it's correctly localized or not. But if you want to compare with the 3D method, I think it is more fair to evaluate only top one image, top one retrieved, and evaluate with the positions. So the graph of the x-axis will be the distance threshold like this, and y-axis will be the rate of correctly localized images. So I was roughly speaking about 2D, 3D methods. But probably the question is, which is better, 2D or 3D? So I have no clear answer yet, but there are some advantages and disadvantages. For the 2D method, the database is simple. It's just images and GPS. But for the 3D method, we have to prepare the large structure from motion, and we save all the point clouds. And if a new image comes, we have to really rerun the boundary adjustment again. But if we evaluate it, it seems 3D method is more accurate. But actually, we presented a paper, a poster, yesterday. Before that, there was no fair comparison between the 2D and 3D method. Because, as I briefly mentioned, the San Francisco dataset has a 3D point cloud and images, so we can compare it. But they provide only the labels, and there were no ground truth camera poses. So in this work, we manually make the feature labeling and compute the ground truth camera pose for the query images. Now we can fairly evaluate 2D versus 3D method. So this is the result of the evaluation, actually. And these two graphs are the 2D methods. And please see these curves, bottom two curves. Those are the kind of 2D methods, state of the art. So this log is Hamming embedding based, Boggle Ball based. And these are the blood-based approaches. So actually, all of them has quite similar performances. But if we compare with the 3D-based method, and if we want to have a accurate localization, 3D method is better. So one of the 3D methods is this green curve. So actually, in the 3D method, the localization rate is like 60% for the 5-meter distance threshold. But for the 2D-based method, it's much worse. This is quite obvious because the accuracy of the 2D method is quite depending on the sampling rate of the database. So if you want to make it more accurate, this is what we recommend. You can retrieve some images from the database and do the local SFM online. And then you can have the more better poses, accurate better poses in 3D space, and register it back to the map. With this method, with this technique, we can improve the 2D-based method quite a lot. Of course, there is a trade-off of the computational time. We have to compute the SFM online. But I think this method could be potentially used for the future pipelines, because then we don't have to really maintain the large global 3D models. So to summarize, so I think there are still some interesting things, even for the feature-based place recognition. And what we still have to think about is, one of the topic is image projection models. In the earlier of this session, I said we just make a cut-outs of the perspective images from panorama, but of course, this does not really cover the whole nice characteristics of the panoramic view. So there could be better representation of the image or better representation of the image descriptors. So I'm quite interested in this direction. And of course, there should be some better CNN-based approach, or maybe the fusion of the feature and the CNN-based. And now I'm currently interested in large-scale indoor localization, which is not really done yet, I guess. There are some, of course, there are many indoor localization, but often it's not really in the large scale. It's typically not too large. And also there will be some, there could be some nice techniques by combining with semantic informations. So that's all from my side. And if there's any questions, yes, please. Oh, so NN means just a standard image retrieval, and SR is with a spatial verification. So we take top 20 images and re-rank it, or maybe top 100. And SR SFM is with the local SFM. Yes, the answer can re-ranking.
Hi. Do you have any papers available, and where could we get them, or code?
So papers?
Papers or code available?
Oh, actually, so here all the methods all the methods codes are available. So you can use disloc, netblad, and so on. It's all available. Sorry. So we have the paper about this. Oh yeah, we will put the links to the code on our this tutorial page. Is that okay?
So I just have a quick comment. If we would appreciate if someone asks a question without the microphone, if you can repeat the question so that we can hear what the question was. Is that clear or not? So if someone asks a question from the audience without the microphone, I would appreciate if you can repeat the question so that we can hear the question.
Okay.
And I actually have a question. So when it comes to unstructured large data sets like the ones you get from, I don't know, Flickr or some internet database, there could be the case where you would have redundant images. So a lot of images taken from the same perspective, same scale, same time, which does not add a lot of information. So how would do you have a method to like prune that to just a set of essential images? Because if you keep a really large database of images, that's not easy to handle. So if you can prune it down to just the essential set of images, that's much better.
So for the organized images, of course, we have to somehow first organize them. And one of the way may be using a structure for motion. And in the structure for motion, there are many ways to find some landmark images when there are too many things. So I think that will be one option, or we can just simply pre-cluster them. Or that's.
Thank you.
Okay. Okay, so thank you for your attention, and so I will conclude my talk now. Thank you very much. Do you want to use mine?
Yeah, sure.
So, hello everybody. I'm Giorgos Tolias from the Visual Recognition Group at CTU in Prague. So, in my talk, I will present methods for visual place recognition, and in particular, for the case that is discussed as image retrieval by using CNNs. So the task has been already presented briefly. What we need to do is to name or recognize the place that is depicted, or recognize the location where an image is taken on the map. Okay, better? Thanks. So the methods that I will present, this is discussed as image retrieval, and in particular instance search. So we're looking after different instances of the same object, building, or street in order to transfer information from a large collection of images, such as tags or geotags, and identify the place. Particularly, many of the methods fall in the case that you extract a single descriptor from the database images, the same for the query, and recognition is performed as nearest neighbor search in high-dimensional spaces. Here just a demo of an interesting scenario where a large collection of Flickr images is indexed. They're all accompanied by user tags or geotags. So when the test image comes, we can transfer the geotags from the relevant images, and identify the location on the map, name the landmark that is shown, or also get relevant information such as the architect that designed this building. So for image retrieval, the story has started with CNNs similarly to other tasks, which is we get a pre-trained CNN, a CNN that is trained for image classification on ImageNet, and use internal layer activations as features. So these appear to generalize quite well in several computer vision tasks, such as detection, scene classification, fine-grained recognition, and so on. So the same happened at image retrieval, and this is what I will cover in the first part of the talk. So how to use pre-trained CNNs to perform instance search. So initially, what was done is to feed an image as an input to a network and use the activations of the fully connected layers as image descriptors, and then use Euclidean distance to perform retrieval. So this appears to work quite well due to the semantic information that such a representation carries. However, some drawbacks are that you had to resize or crop the input images to a fixed size. And such a representation is not translation invariant, as the positions of the activations of the preceding layer, the convolutional layer, are directly encoded into the feature vector. So then what was done is that the fully connected layers are discarded, and we're dealing with a fully convolutional architecture. We're getting a 3D tensor of activations out of a convolutional layer, And there we perform global max or sum pooling to construct an image descriptor. So a single scalar per feature map is kept, the sum of activations or the maximum activations, and the dimensionality of the descriptor is equal to the number of feature maps at this convolutional layer. The benefit is that we're dealing with a fully convolutional architecture and we can feed images of any aspect ratio or any resolution, and that this representation is translation invariant. Further improvements are obtained by appropriately weighting this 3D tensor of activations. One weighting is performed like feature map-wise in an IDF manner as the inverted document frequency typically used in information retrieval. And another weighting is performed for each spatial location by using the L2 norm of the vector of activations of all feature maps at this location. And in this way, we obtain a saliency mask to appropriately weight each location and downweight background information, for instance. So now I will focus on the representation that is constructed by global max pooling that I mentioned before, the MAC descriptor from maximum activations of convolutions. So what is done here is that we see the 3D tensor of activations as a set of 2D maps of responses, one for each feature map. For each one we perform global max pooling. We choose the maximum activation, a single scalar to store at one component of the image descriptor. So this activation is also associated with an image region, which is the receptive field of the maximum activation. Now to compare two images, to evaluate the similarity of a pair of images, we simply compute the cosine similarity of two MAC descriptors. Now when we're comparing like two images with a similar object, the same object depicted, we expect the maximum activation to be spotted on the same part of the object. Here in this example, we visualize the corresponding regions, the receptive field size of one feature map with the same color, and we see that implicitly some correspondences are formed between image regions that are somehow like they're roughly well localized, and this gives some understanding of why such a representation of a pre-trained network works. Further improvements are obtained by considering again the 3D tensor of activations of a full image, but then considering like multiple regions uniformly sampled in this case at multiple scales, and from each region we construct a MAC descriptor and sample all the regional descriptors. So in this way we end up with the same dimensionality as the MAC descriptor, but by incorporating like regional representation, this descriptor better handles small objects, partial matching, and severe occlusions. For such descriptors and for the descriptors that I've mentioned before, it is known that applying further post-processing is essential. So one typical pipeline is L2 normalizing the descriptor, performing whitening of the feature space, and then renormalizing. So a common case is using PCA whitening that basically transforms the distribution of the data points into a unit sphere. So for such a representation, it is known that there is some redundancy of different feature maps. So apparently the decorrelation performed by such a whitening significantly helps and improves the performance. Now to see a comparison with such a descriptor, which is a compact image descriptor, we have a global image vector, one descriptor per image, compared to prior work on compact image descriptors based on local features. The descriptor from a pre-trained network already does much better. This is comparing like the third and the fourth row of this table, while also compared to more memory demanding approaches based on local features that are dealing with indexing separately several thousand of local features per image. Their MAC representation already does better in some cases, despite in the simplicity of the approach, the efficiency of the search, that like you simply do nearest neighbor search with a global image descriptor. So the evaluation in this case is performed on Oxford buildings and Paris datasets, which are like containing buildings and landmarks, which are close to the task of place recognition. Let me know during the talk if there are any questions. So, to what I presented before, we extract a global image descriptor to represent an image. Now we are exploiting the same information from the 3D tensor of activations in order to get a query image and localize the object on the database side. So this is done without any supervision. There's no learning involved. We approach this as a sliding window matching. So what we propose to do is to obtain a very efficient way to construct the MAC descriptors for any possible region of an image, and then evaluate MAC similarity in a sliding window manner. For the MAC descriptor, we need to perform max pooling over an image or a region, and here we employ the generalized mean. So instead of computing the maximum value of a set of responses, we raise each response to the power of alpha, sum, and then raise to the power of 1 over alpha. So this quantity here goes to the maximum as alpha goes to infinity. And we see that we can get like good approximations of the maximum even with values of alpha around 10. Let's see this in a toy example. We have a 2D map of responses, a candidate region. To construct the MAC descriptor, we need to compute the maximum value, which we directly compute here in an exact way. And then, in the example here on top right, we raise all activations to the power of 10. We sum all activations in the candidate region, and then raise to the power of 0.1. That's a generalized mean for alpha equal to 10, and we see that we get a good approximation of the maximum value. Now, what is the benefit? The benefit is that in order to approximate the max, we have a sum of terms, which is directly compatible with using integral images, and we obtain the maximum with a simple sum of 4 terms for any candidate region. Now, how do we apply this for image retrieval? We have an initial ranking stage with the global descriptors. So we're searching after like a query defined with a bounding box here, and then we apply this localization scheme in a re-ranking phase. So we only apply it in the top ranked images to localize the query object, and then we obtain an improved similarity that is not distracted by background information. So in this way, images that before, due to the use of a global image descriptor, were lost, now they're re-ranked in top positions. Such a method, when applied for re-ranking on 1,000 images, takes less than 3 seconds on a single CPU thread. Such a localization further improves the performance of such a pre-trained CNN-based approach. Just to mention that there are also more approaches that see this 3D tensor of activations as a set of dense local features extracted from a CNN, and then they apply popular encodings from local feature-based approaches, such as bag of words, Fisher vectors, and VLAD. And I will not get into more details for these approaches. So to summarize so far, what we saw is what is also done in other computer vision tasks. A pre-trained CNN trained on ImageNet. We use the activations of internal layers to construct an image descriptor. So what is also known by other computer vision tasks is that further training, the so-called fine-tuning with training data and a loss like closer to the target task, can significantly improve. And this is what I will cover for the case of image retrieval and CNN fine-tuning in the second part of the talk. Are there any questions so far? Okay. So, a standard recipe, we collect a large collection of images from the web, and then we need typically to put human in the loop, create image annotations, construct a training set, and perform the fine-tuning. One way to achieve this is employing Mechanical Turk. It's not so accurate. It costs some money. There are also other ways to employ experts to perform this labeling that costs even more money. And here we're going to talk about automated ways to extract training data to perform the CNN fine-tuning. In particular, here we will use methods like Aki presented in the previous talk, handcrafted approaches, methods that we understand in a better way and they're well tuned for this task. So we'll use such methods to provide algorithmic supervision in order to collect training data and perform the CNN fine-tuning. So before doing so, let's see so far what are the kind of annotations that have been used to perform CNN image retrieval. The first category is what I presented, is a pre-trained CNN. It is trained on ImageNet. ImageNet has 1,000 classes. Here we see the building class, which is also like our concern in the case of place recognition. So we see that all buildings belong to this class, so they are considered similar to each other, which is far from what we need to do in this task of instance search. Then, one step further is the work by Babenko and colleagues that performed the fine-tuning with a dataset of landmark classes. So now, each class consists of a particular landmark, which gets one step closer to the target task. However, still, not all the images of the same class share the same viewpoint. They don't depict the same part of the building. So again, it doesn't reflect exactly what we need to do in the target task. Then, the NetVLAD approach employs weak supervision provided by a large collection of images that carries GPS information, such as street view images. So let's see some more details about the architecture of NetVLAD. It uses a fully convolutional architecture. So at some point, we get the 3D tensor of activations that can be seen as a dense set of local features. Then this is given as input to a VLAD layer that performs the aggregation, and in this case, it is designed in a way so that it's differentiable and the whole network is trainable in an end-to-end manner. So NetVLAD uses a triplet loss, which is a ranking loss, that is already much closer to the target task of instance search than what cross-entropy loss that was used in the prior work. So for triplet loss, we need pairs of matching and non-matching images. Let's see how the GPS supervision is used to construct such pairs. So given an anchor image, any image that is geographically far can be safely considered as a negative one. And there we have a non-matching pair. In the case of matching pairs of positive images, we have an anchor image, and nearby images are considered as candidates for positives, but there is some ambiguity because the camera orientation is not known, but only the camera position. So this ambiguity is resolved by choosing the image that is closest in the feature space. So NetVLAD is already closer to the target task, doesn't involve human in the loop to collect annotations, but assumes that there is a large collection of images that carries GPS information. Now I will talk about automatic ways to obtain such annotations that are accurate enough, and we will focus on using hard positive and hard negative examples. So we employ a large-scale structure for motion system that uses image retrieval to get improved 3D reconstructions. The image retrieval pipeline consists of bag of words with smart codebooks, geometric matching, and query expansion. So this whole system runs in an automatic way in a large collection of images, more than 7 million images, and results in more than 700 3D models that we will use to collect our training data. So for each 3D model, the geometry of the scene is known. We know the camera orientation for a pair of images. We can decide whether, we know the number of inliers, so we can decide whether they have overlapping viewpoints, whether there are true positives. Let's start by the way we choose the hard negative examples. So a pair of images is considered negative, in our case, if the two images belong to different 3D models. We also remove overlapping 3D models so that we can use the labeling safely to mine the negative examples. Hard negative examples are considered the negative ones that are close in the feature space with the current CNN representation. Now, given an anchor image, we consider the most similar CNN descriptor to take the hardest negative example that comes from a different 3D model. In case we want to provide like more negative examples for this anchor image, we can take the most similar CNN descriptors. However, this typically includes some redundancy because the same visual structures coming from the same 3D models will be typically top ranked in the feature space. So once more, we employ the labeling by the 3D models and choose one negative image from a 3D model to remove this redundancy and increase the diversity of the training data. So using hard negative examples is also common in general metric learning scenarios. However, using hard positives is not so common because of the high intra-class variability. So in this case, we will use the geometry of the scene to resolve this and also be able to choose hard positive examples. So positive examples, a positive pair of images, are images that share 3D points. They have overlapping viewpoints. So for an anchor image, a baseline method that we use and evaluate is considering candidate positives from the same 3D model. However, not all of them share similar viewpoints. And to resolve this, we choose the closest descriptor in the feature space. This is what we used in EdVLAD to also resolve the ambiguity of the GPS information. This typically will end up with true positive examples. However, the drawback is that we provide something that already the network can recognize since these images are closed in the feature space. To provide some complementary information, we use the 3D geometry of the scene, we use the number of inliers, and we choose the image that comes from the same 3D model and has the maximum number of inliers. So that's something complementary and something that the network cannot necessarily already recognize. We relax this a bit, this constraint, and choose a random image from the top matching ones based on the number of inliers to get more challenging viewpoints. So in this way, yes? Okay. In our case, we have fixed hard positive examples, but we keep reminding, as is typically done with the hard negative examples, which appears to be essential. So a few times per epoch, we have fixed anchor points and we keep reminding the hard negatives. We have the label from the 3D model, so we know which are the negatives, and we just choose the closest one in the feature space that keep changing after the parameter update. The positives are fixed in this case, yes. And the positives, according to the way that we choose them, based on the geometry, will not change after any parameter update. So about the architecture that we use, it is basically what I presented before, a fully convolutional architecture that we perform global max pooling to construct the max descriptor, and this basically gives us an embedding of an image to a vector, to a descriptor. We have a CMH architecture, two branches that share the same weights, and finally use contrastive loss to compare pairs of matching and non-matching images. In the case of matching images, the loss increases according to the Euclidean distance of the descriptors, while in the case of non-matching pairs, the loss is high if the descriptors are close in the descriptor space, while the loss is zero if they're already far enough. So I've mentioned before that further post-processing is typically shown to be essential and very effective of such descriptors. So a common case is, either we use a pre-trained network, or like we perform the fine-tuning, the training is done, is finished, and then we consider further post-processing of such descriptors. A common way to go is learning the PCO whitening in the unsupervised way. However, in this task, we already have labeled data, labeled pairs, and with these labeled pairs, we learn the whitening in a discriminative way with the supervision offered by the 3D models. We also see that this is better than trying to learn the whitening in an end-to-end manner, and also much faster to compute. So now some experiments, again on Oxford and Paris datasets. We have the off-the-shelf representation that are presented in the first part of the talk without any fine-tuning. And then we see that by considering our training data and fine-tuning the network, we have a big increase in performance and further increase for harder and harder examples, and also with the supervised whitening. So the final increase is significant compared to the off-the-shelf network that was trained on ImageNet. So what did we do here? We used a more sophisticated, let's say, retrieval and structure from motion pipeline based on local features in order to provide algorithmic supervision for the training. So this is the system that we call our teacher for the training. And it's a memory demanding system that needs to index several thousand local features per image, their appearance, and their geometry. Well, in this case, we learn a compact image representation with the CNN, and we see that such a representation even manages to outperform the teacher when it's combined with ranking and simple query expansion, like in the case of average query expansion. There is another work that also uses automatic ways to collect training data and fine-tune the RMAC representation. So in the corresponding archive report, it's interesting that they show how quantization-friendly such a representation is, in particular with using product quantization, as we see here, where the performance is nearly unaffected for highly compressed CNN descriptors. So we have improved the performance, several cases in the benchmarks that we evaluated. However, there are some cases that are not handled well with the fine-tuning. We construct a global image descriptor that is not able to capture well like small objects. That, in the example that I saw here, we have a query that is a small region of an image, and Boggle Ball with geometry is able to successfully retrieve the relevant images, while the top retrieved images with the CNN and the global descriptor are all incorrect. So in the next part of the talk, I will talk how to use fine-tuned features. So the training is finished, there's no more learning involved, and we will use query expansion approaches to improve some of the cases that fine-tuning is not able to handle well. Do you have is there any question before I continue?
So in the past section, did you either train on any, looking at variances in lighting, season, any of that, or you just kind of ignored it?
Sorry, can you say again? Okay.
In terms of invariances in season, lighting, other things like that.
Okay, we don't try to control what kind of data and what kind of variance we'll have in this sense. However, such variance will be included in the training data because of the way that are sampled with geometric matching up to some extent.
Okay. Did you evaluate on how it did in some of those conditions? Did you see the deep learning stuff didn't do as well across season? Maybe it did okay in lighting?
Well, we haven't done let's say quantitative evaluation in this aspect. However, we have internal demo that compares the two approaches on large-scale datasets. And for instance, we have seen that the CNN can handle much better large illumination changes, matching day images with night images that it's difficult to handle with local feature-based approaches.
Okay, thanks.
So with what is presented so far, we learn an image embedding and then use Euclidean distance to perform the image retrieval, which is not always appropriate, such as in the case of severe visual variations, that the different instances of the same object will lie on a nonlinear manifold. So here we employ graph-based methods such as diffusion to perform ranking on manifold, query expansion, and improve the retrieval performance. So we use diffusion approaches. The most well-known one is PageRank. In particular, we use the flavor of Zoo and colleagues. So what is done in this case is that we construct a k-nearest neighbor graph of the image collection. Each node is an image and the corresponding CNN descriptor. So the corresponding affinity matrix, the normalized affinity matrix of such a graph, defines in a random walk, in a random surfer scenario, the probability of jumping from one node to the other. Also, we define what is the query of the search by corresponding vector that has like a non-zero element to define which node is the query. And the solution comes in an iterative manner with a mixing parameter alpha that defines the probability of performing the jumping from node to node or randomly jumping back to the query image. So what we obtain as a solution is a vector of similarities of the query to every image in the collection, to every node of the graph. So let's see now in a toy example here, in a 2D toy example, what this similarity captures. Here we see a set of 2D points. The blue points are like the collection that we are indexing, and the green and the red point is the query image. It's the query node. Finally, we saw with isocontours the similarity of the diffusion that we obtain that appears to capture the manifold that the query belongs to. So that's quite different from what Euclidean distance would do to perform image retrieval. Also to mention that this scheme is very easy. It's like straightforward to extend it to multiple queries. You simply like have multiple non-zero elements in the vector y. Finally, in the literature, like in the work of Zhu et al., they saw that like there's a closed form solution of such an iterative scheme, but this is typically avoided in the literature because it involves the inverse of a sparse matrix that is not sparse anymore, so that's difficult to compute and store in large-scale problems. What we also see is that in the prior work, there is an assumption that the query is part of the graph. That's a bit an unrealistic assumption because the query is not available in the offline stage that we construct the graph. So what typically somebody has to do is to, when the query comes, update the k-nearest neighbor, append it to the graph, renormalize the matrix, and then perform the diffusion, which should take some time and might also require extra information. So what we say is that instead of searching for the query, we search for the nearest neighbors of the query, which are already part of the graph. So in the toy example here, instead of searching for the red point, we search for the green points that are the nearest neighbors of the query. And as I said, it's straightforward to extend to multiple queries, so we simply define multiple nodes to be the queries of the graph. Diffusion is performed similarly, and the solution that we're getting is not very different from what we were getting before. Moreover, in the literature, the iterative solution is typically performed, which is a bit inefficient and takes some time to converge. The closed form solution is avoided. However, we propose to solve the equivalent linear system that involves a sparse matrix, and we solve it with conjugate gradient. So again, conjugate gradient gives an iterative solution, but we observe that it converges much faster. And also in our work, we saw that like the previous scheme is equivalent to Jacobi solver that is known to converge slower than conjugate gradient. Also, a remark is that we're not looking for like, let's say the exact solution, but we need a good ranking of our images. So that means that we can also stop this iterative process a bit earlier. So far, we're dealing with global image descriptors. So one node is an image, and this is something that is also commonly done in on image retrieval, where diffusion methods are applied in the past also with traditional methods based on local features. So we propose here to construct a KNN graph where each node is an image region and the corresponding CNN descriptors. So as in the case of RMAC, we extract a descriptor from a region, but we index them independently instead of aggregating them. when the query comes, it also consists of multiple regions and multiple descriptors. So again, we are searching not for the query descriptors, but for their nearest neighbors, and define multiple queries on vector y. Diffusion is performed in a similar manner, but the solution that we're now getting is a vector that has a similarity for every image region. We simply obtain image similarity by pooling over multiple regions. Going back to the toy example, here we have like 2 query points, the red points, and we see that like finally the similarity will capture manifolds, multiple manifolds that the query descriptors belong to. We apply this on image retrieval, and we see that the regional diffusion significantly improves for the case of small objects that were previously not retrieved well when they take only a small part of the image because of the use of global image descriptors. So in particular, we measure the performance versus the relative object size and see significant improvements when the relative object size is quite small. Let's go back to the different solutions for diffusion. The iterative one that is typically preferred in the prior work. The linear system that also involves a sparse matrix, and we propose to solve with conjugate gradient. And then we also have the closed form solution that involves a matrix that is not sparse, the inverse of the Laplacian here. However, imagine that in the case of a small scale scenario, somebody can pre-compute this matrix in an offline stage, and when the query comes, you construct vector y, and then diffusion is very efficiently performed, since it's a simple linear combination of the columns of this matrix. Now, we focus on this solution again for even large-scale problems. I will not get into many details, but we propose to approach this with a low-rank decomposition of such a matrix. But the nice part is that we never have to explicitly construct this matrix that is not sparse and it's large to compute and store. So finally, due to the low rank decomposition, we perform like approximate eigen decomposition. There are methods to perform approximate eigen decomposition of such a large matrix. So finally, diffusion on query time is efficiently computed by two matrix-to-matrix multiplications. What we see in the experiments is that compared to the previous solution with conjugate gradient, we are 2 orders of magnitude faster with such a solution, such embeddings to perform manifold search and maintain somehow more or less the same performance. Let me know if there are any questions before I proceed to the last part of the talk, where I will describe methods that use, again, features that are already trained, fine-tuned for image retrieval or location recognition. And we propose here we are dealing with a representation that is well adapted to the task of location recognition. So here on the left, I show the traditional approach of extracting a descriptor from an image, also for the query, performing nearest neighbor search, and then transferring the location of the retrieved images to perform location recognition. On the right, we assume that we have several images associated with a location on the map, which is a realistic approach since in many cases location recognition is handled with street view datasets on the collection side, on the database side. So what we propose to do is to jointly represent all these images with a single vector representation. We also assume that a set of images is associated with the query location. So that's again a realistic assumption when we're dealing with self-driving cars. And for the case of a mobile user, we will later see that like even if we have like a sparse view of the location, just a few images, this will still work. So we have a joint representation for each location and for the query, and again we can perform nearest neighbor search since each descriptor is associated with the same location. So the first simple method that we try is to perform auto-stitching with local features and geometric matching. We perform auto-stitch and construct a panoramic view of each location. So here what we see is that we see the 24 images that are available associated with each location. It provides a full 360 view, a panoramic view, and with two different yaw directions. So we construct the panorama, and then we simply feed this to NetVLAD to construct like an image representation that now represents the whole panoramic view of the location. So that's what we index, and that's what we construct also for the query image to perform image retrieval. Now we further propose to construct an implicit representation for such a panoramic view. We use again NetVLAD. There's no training involved. NetVLAD is already trained, as in the original work, it's trained for location recognition. But now we use it to construct an image descriptor for each of the 24 views and propose to construct the joint representation in the feature space. So we use two ways. One is simple sum pooling, and the second one is what I will explain now and we call pinf pooling. So let's consider that we have each descriptor of an image in a column of matrix X. So sum pooling is simply the sum of all columns, and we get a single descriptor for the location. Now in what we call pinf pooling, that was previously tried only on the database side to jointly represent a set of images, is computing the pseudo-inverse of matrix X and then summing all the rows of the matrix to get a single vector representation that has the same dimensionality as the NetVLAD descriptor. Let's see in a toy example what happens when we will match with inner product two such joint representations, so two vectors that are associated with two different locations, and evaluate their visual similarity. So in the toy example here, we consider two locations, the green one and the blue one, each consisting of 8 images and 8 corresponding descriptors. So that's a 2D toy feature space. In the case of sum pooling, when we compute the inner product between two such vectors, this is equivalent to computing the similarity matrix for all pairs of descriptors and then summing the similarities. So here we also depict what happens in the case with the similarity matrix in the case of pinf pooling. We can see that pinf pooling is somehow approximating an one-to-one matching scheme. So let's see this case where we have like one descriptor from one location close to 3 descriptors from the other one. In the case of sum pooling, we see the 3 large values here, so we have like 3 large similarities, so it's like one-to-many scheme, while in the case of pinf pooling, this is closer to one-to-one matching and we'll have only one large value. This is the case also for the 3x3 group shown here, that results in a 3x3 matrix, submatrix here with large values, while here the large values are concentrated on the diagonal, again being closer to a one-to-one matching scheme. So that gives some more understanding of why such a representation works well. Now we also consider the case that we don't have like a full panoramic view, a full 360 view, which is closer to a mobile user scenario. We just have some of the images available. The implicit representation is directly applicable. We just perform the pooling in the feature space. Now we also propose an additional intermediate solution. So we consider NetVLAD to be composed of 2 parts. The fully convolutional parts that gives us a set of dense local features, and the VLAD layer. So what we simply do is that we feed all images to the first part, get a set of local descriptors from each image, merge them all, concatenate them, and then feed them all in the VLAD layer that will perform the pooling and will provide us a single vector for all the images. We evaluate such method on Pittsburgh dataset. It's evaluating like location recognition. So we see that all the proposed methods significantly improve the performance and achieve near optimal performance in this task. Moreover, we see in the case of the sparse, on the sparse panorama, that we consider it only on the query side to be more realistic in a mobile user scenario. That only 4 views are enough to get, again, near optimal performance with both methods. So just to overall now summarize the methods that I presented in the talk, we started with using pre-trained CNNs on ImageNet, and we saw that they allow us to construct compact image representations that already generalize well in the task of image retrieval and location recognition. Then we saw how fine-tuning can significantly improve, and it's interesting that for such a task, we have automatic ways offered by traditional methods based on local feature geometry, so we have automatic ways to collect training data and not involve a human in the loop at all. Finally, with cases that fine-tuning might not be enough, we are improving the performance with manifold search based on query expansion approaches. And in the end, we saw that there are cases of a representation well adapted to the tasks that can significantly improve place recognition. I would like also to thank collaborators with whom we've worked in the work that I presented in this talk, people from Rennes, Paris, and Prague. And finally, there is online code for several of the methods that I presented in this talk. Thank you. You can let me know if there are any questions. So if there are no questions, now it's time for a break until 11:15. We're continuing with methods for image-based localization, starting from local feature-based approaches and then deep learning-based approaches.